Okay, welcome back. This is now the 8th lecture of the condensed matter course. One of the more wonderful things about quantum mechanics is that particles are waves and waves are particles. And that means the things that we learn when we study vibrational waves in solids can often be applied to other types of waves in solids, such as electron waves or even electromagnetic waves. So today we're going to be studying electron waves in solids, and this lecture is a little bit out of place because later on in the course we're going to spend several days studying electron band structure, electron waves in solids in some amount of depth. But the reason I'm inserting this lecture here is to make the point that we're really studying the same thing, whether we're studying vibrational waves or we're studying electron waves. It's really very, very similar. We're also going to see that much of the calculation we do today is similar to what we did when we studied the covalent bond, which was a wave just between two atoms. So the picture we're going to look at today is a one-dimensional tight binding chain. And it's going to be very analogous to the one-dimensional vibrational chains that we looked at in the last couple lectures. Also similar to the covalent bond. So we're going to imagine having a bunch of nuclei in a chain like this. And we'll give them a lattice constant A, distance between identical nuclei. And we're going to add one electron to this chain of nuclei. And we're going to see what happens as we allow the electron to hop back and forth between the different nuclei. So of course we have to start with a Hamiltonian as the usual p squared over 2m term, plus it will have an interaction with all of the different nuclei, v of r minus r sub j, where r sub j is position of nucleus j. And as I did when we studied the covalent bond, we're going to abbreviate these terms for convenience. This term will be called K for kinetic energy, and these terms will be called V sub j for interaction with the jth nucleus. Now, similar to what we did when we studied the covalent bond, it's useful to think first about an electron only interacting with a single nuclei, not with any of the other nuclei. So we'll write we'll write K plus V sub m as our Hamiltonian, and that means that the electron has its kinetic energy and it's interacting with the mth nucleus only. And we'll give it E atomic when it interacts with nucleus m only. So the eigenstate of the Hamiltonian, which has it interacting with the mth nucleus, we'll call that the ket m, and that will put the electron on the mth nucleus as if all of the other nuclei were not there at all. So we'll label this ket 1 if the electron is sitting here as if it and not interacting with any of the other nuclei. We'll call this one 2, this one 3, and so forth. Okay? Happy so far? Okay. All right. Now, as we did when we studied the covalent bond, we're going to make a bad assumption, which is that these kets and an m are orthonormal. This is not too bad if the nuclei are far apart from each other, because an electron sitting over here and an electron sitting way over there are pretty much orthogonal to each other. But when the nuclei get close together, then they're not orthogonal anymore. And the reason we make this approximation, even though it's a bad approximation, is for simplicity. A lot of the calculation just gets a lot easier if we make this assumption, and you don't learn a whole lot more from doing it more properly. It's not that much harder to do it properly. There's an exercise in the book that walks you through it, and you can go through it if you want, but you'll get most of the interesting physics out of just this simplified approximation. Okay, so once we have made this bad assumption, we can write down our trial wave function. Trial wave function, very similar to what we did with the covalent bond, which will have the form psi equals sum over n phi n n, a linear combination of atomic orbitals, which is a word we used equivalent to tight binding, linear combination of atomic orbitals, or LCAO. We have a bunch of atomic orbitals, electrons sitting on each nucleus, and we're going to make a linear combination of them with coefficients phi sub n. The reason people love this type of approximation is because you can make it more and more accurate by just adding more things to the right-hand side with variational parameters phi in front of them. So for example, you could have an electron sitting on site n in excited state alpha. So this could be 1s, 2s, 2p, so forth and so on. And we can just make our basis state bigger and bigger, basis set bigger and bigger and bigger, and give all of these coefficients. And as we make the basis set bigger and bigger and bigger and bigger, we get a more and more accurate approximation of the true wave function. Okay? So it's a sort of a variational approach. So we can solve for the ground state by finding the best coefficients. Then once we have the ground state, we can solve for the first excited state by finding the best coefficients, the lowest energy coefficients, subject to being orthogonal to the first thing that we just found, and so forth and so on. So now what we have to do is we have to write down a Schrodinger equation for these coefficients. And the Schrodinger equation, again, something that you will solve for in your homework, will be of the form h n m phi m equals E phi n. It looks like a Schrodinger equation. It quacks like a Schrodinger equation. It probably is a Schrodinger equation. It's not the real Schrodinger equation, because the real Schrodinger equation has the full Hamiltonian sitting here. Here, instead, we just have a matrix, n, h, m. And you can think of this as being the projection of the true Schrodinger equation onto the basis set made up of these kets n that we're working with. Okay? Does that make sense? It looks like a Schrodinger equation. It's going to act like a Schrodinger equation. And you'll derive it also. Okay. So given our Schrodinger equation over here, we have to now calculate these matrix elements that go into our Schrodinger equation. So let's do that. It's useful to take our Hamiltonian and divide it up into pieces. So first, we'll remove the interaction with the mth nucleus from the interaction with all the other nuclei. So this will be j not equal to m, v sub j. The reason we do this is because then we can write h on the ket m equals k plus vm on the ket m plus the interaction with all the other nuclei v sub j on ket m. Okay? Now, we defined the ket m to be the eigenstate of k plus vm. So this thing here is just E atomic on ket m. Good? Happy with that? So then we can take the inner product, close up the inner product with the ket n over here, and we get E atomic delta nm plus n sum over j not equal to m v sub j m. And this is the interesting term here. So this term here just tells us that no matter what site the electron is sitting on, which nucleus the electron is sitting on, it has energy E atomic. And this is all the interaction with all of the other nuclei. Now, there's a couple of things that could happen with this term. One possibility is that n equals m, in which case what this is telling you is that there's some change in its energy sitting on nucleus m due to its interaction with all of the other atoms, not m. Okay? So this will be, we'll give this thing an energy, we'll call it v naught equals n sum j not equal to m, n, I guess these could be m's, like that. And this is interacting with all the nuclei, not including m, and it's an expectation of its energy. So it's just shifting its energy on that particular site. That's not particularly interesting. The more interesting thing is what happens if n not equal to m. So in this case, you have this term is, or maybe I should call this term something first. This is what we called direct before, and I guess I call it v cross when we talked about the covalent bond. For the n not equal to m term, this is what we called hopping before. And the reason we called it hopping was because, and we'll give it the value minus t, the reason we call it hopping is if you think in the time-dependent Schrodinger equation type of way, you can take an electron sitting on site M and have it end up on site N. So this off-diagonal term in the Hamiltonian allows an electron to move from one site to another, hence we call it hopping. Now, an approximation, which is actually a fairly good approximation, is that n minus m greater than 1, hopping is 0. Hopping equals 0, or is approximately 0. And the reason for that is because it's very hard for an electron to hop very far in one step. If you think about it for a second, what we're really calculating when we take this matrix element is some sort of, when we write out the matrix element explicitly, it's something like this. Right? This is what matrix elements look like, a bra, a ket, and an interaction. Now, if n and m are far apart, these wave functions decay very quickly as you go away from the nucleus. So there will be no point in space where both this is large and this is large if the two nuclei are very far apart. So that's why we can assume that this matrix element is going to be 0 unless n and m are essentially neighbors. Okay? Good? So what we have now is we have this, in the end, we have that we can write n sum over j not equal to m v sub j m equals the direct term v naught if n equals m. We'll call it minus t if n equals m plus or minus 1. So we can hop one site only and 0 otherwise. Okay? Good? Are people happy, fairly happy with that? Good? Yes? Someone nod. Someone say yes. Yes. Thank you. I would send you another chocolate, but I gave you one yesterday. Right? So, okay. Good. So we can take our Hamiltonian and rewrite it as H as a big matrix. H n m equals, what is it? It's E atomic plus the interaction with all the other nuclei, not including site itself. If you're sitting on one site, interacting with all the other ones, not including yourself. Plus, there's going to be another term, which delta n m plus 1 plus delta n comma m minus 1. So there's this additional term here, which allows you to hop one step to the left or one step to the right with an amplitude t. Okay? Good? So this is a great big matrix. If we have, let's say we have n nuclei to begin with, then H is an n by n matrix, n by n Hamiltonian matrix. And we need to find its eigenvalues. So how do we do that? That looks like a complicated problem if n is a pretty large number. Well, again, we can solve this very similar to what we did for the vibrational chains. We use an ansatz, which is an English word, ansatz. And the ansatz we use is a plane wave ansatz, I, K, N, A, like this. Now, a couple comments about this. First of all, you may be expecting an e to the I omega t from what we did with the vibrational chain. The reason there's no e to the I omega t is because we're solving the time-independent Schrodinger equation, not the time-dependent Schrodinger equation. If we were solving the time-dependent Schrodinger equation, there'd be an e to the I omega t as well. Okay, that's why it's not there in this case. It's just simpler in quantum mechanics to work with time-independent eigenstates than it is to work with time-dependent wave functions. So that's the first thing. Second thing is that you probably, if you're careful, you put down a square root of capital N downstairs so that this is a normalized wave function. The normalization isn't going to matter much for us, but strictly speaking, it should probably be there. And the third thing to note is that this wave is the same if you shift k to k plus 2 pi over a. This is something we discovered last time. The thing that's important is not the momentum, but the crystal momentum. If you shifted k by 2 pi over a, I'd get back exactly the same wave. Okay? So let's take our ansatz, plug it into that Hamiltonian. One step here, we get epsilon naught e to the minus I k n a minus t e to the minus I k n plus 1 a plus e to the minus I k n minus 1 a equals e to the minus I k n a. So that's just plugging the ansatz into the Schrodinger equation using that form of the Hamiltonian. Okay? So this is the oops, I didn't tell you what E naught is. Sorry about that. This thing here I called E naught. So this is the energy on site. This allows you to hop to the left, hop to the right, and this is the eigenenergy on the other side. People happy? Okay, good. Thank you. Good. So then you just cancel out a bunch of factors, a bunch of exponential factors, and you get E is E naught minus 2t cosine Ka. So let's actually plot that. Here we go. So here's pi over A. Here's minus pi over A. Maybe this is energy on this axis. Energy, this is E naught. And then we'll have a nice cosine form that looks kind of like this. Looks kind of like this. And if you wanted to, you could continue it out periodically further. But what we're really interested in is the waves within the Brouillon zone. Brouillon zone from here to here. Because once we go outside of the Brouillon zone, we're just reproducing the same waves over and over again. And if we want different waves, all the waves within the Brouillon zone are different from each other. But once we go outside of the Brouillon zone, we start repeating things that we've already considered. Okay? Just a bit of nomenclature, which is fairly useful. Maybe I'll put it over here. An energy band means one eigenstate at each k in the Brouillon zone. So here we've drawn an energy band. Now you remember this looks a little bit like what we got when we solved the monatomic harmonic chain, the vibrations of a single chain, of where every atom is exactly the same and every spring is exactly the same. Last lecture, when we solved the diatomic chain or the alternating chain, we found that there were two branches of excitations. There were two normal modes at each k vector, k in this direction. If we had something similar in this picture where there were two eigenstates, a low energy one and a high energy one, we would say that there are two energy bands, a low energy one and a high energy band. We do not use the words acoustic and optical when we're talking about electrons for reasons that will become clear in a moment. But it is useful to compare this dispersion to what we got for vibrations. The monatomic chain. Monatomic. We had omega squared equals, I guess it was 2 kappa over m minus 2 kappa over m cosine Ka. I believe it was equivalent to that. And you'll see that the two dispersions look awfully similar, but there is a notable difference. And the notable difference is that with the Schrodinger equation, we got E on the left-hand side, and with the vibrational chain, we had omega squared on the left-hand side. The origin of this difference is that the Schrodinger equation, if you think about the time-dependent Schrodinger equation, it has one time derivative, whereas Newton's equations, F equals ma, the acceleration is two time derivatives. So that's why we're getting two frequencies over on the left-hand side, but only one energy on the right-hand side when we're thinking about Schrodinger. And that actually makes a rather important distinction between the two. When we had the vibrational chain, at low energy, we got linear modes coming in down to zero frequency at zero wave vector. In this picture here, in the electrons, in the case of electrons, if you expand near zero wave vector, it's E naught minus 2t, and then they'll substitute in for small wave vector Ka squared over 2, like this, we see that we get, 2t here. What we get is constant, which I'm not interested in, plus Ka squared times t. It's quadratic at low energy, as you would expect from a cosine. And that's why we do not use the word acoustic for these low energy modes for vibrations. Acoustic modes, by definition, sound modes, have linear dispersion that the frequency should be proportional to wave vector. That's the definition of sound. So here it's quadratic, so we don't call it acoustic, and we don't call it optical either if there's higher energy branches. But this picture of the energy being quadratic in wave vector should be fairly familiar to you from other contexts. For example, if you have a free electrons, an electron in outer space flying around or something, its energy is some constant plus h bar squared k squared over 2m. K squared over 2m. Right? It's also quadratic in K. You might choose C to be 0 if you wanted to, or you could choose it to be mc squared if you're thinking about its rest mass energy as well. But the important thing is that it's quadratic in wave vector, the same as this electron over here. So it might be useful for us to sort of think in terms of free electrons for a second. And so what we do is we define an effective mass m star, such that h bar squared over 2 m star equals a squared times t. With this definition, then for our energy band, for electrons in our energy band, we still have energy equals a constant, same constant, plus h bar squared k squared over 2 m star. Okay? It looks just like free electrons. It's still quadratic in K, or at least at small k, but now it's an effective mass, m star, rather than the real physical mass of the electron, m. Okay? Now, this, you should really think about this for a second. The effective mass that we're getting here in this tight binding chain that we're solving has nothing to do with the actual mass of the electron. It actually has to do with the hopping between nuclei. For greater hopping, the mass gets smaller. For smaller hopping, the mass gets larger, I think. And so it's totally unrelated to the actual physical mass of the electron. You will find systems, actual physical systems, metals or whatnot, where the mass is 100 times less than the physical mass of the electron, or 100 or 1,000 times more than the physical mass of the electron. Although it's not uncommon to have effective masses in real materials which are on the order of the actual mass of the physical electron. The other thing to keep in mind here is that the K we're talking about in the energy band is not momentum, but it's crystal momentum. Crystal momentum, or h bar k is crystal momentum if you put the h bar in, which means only that we're only defining our momentum modulo the crystal wave vector, the reciprocal lattice wave vector, 2 pi over a. If I shifted everything by 2 pi over a, I'd get back the same physical wave. So it's slightly different from the free electron waves that we're familiar with. The last thing that I want to emphasize here are the eigenstates. Eigenstates are waves, are plane waves, are just waves. Now, why is that interesting? It means that I could take an electron, and if I put it in some state here, it's sort of a right-moving wave. It's a right-moving wave, and that right-moving wave extends clear across the system. It's an e to the I k a n, our form of the wave, which I've, I guess, scrolled off the top of the board. But it's a plane wave that goes clear across the system. And that might be surprising for a second. Why? Well, remember when we studied Sommerfeld theory, there was this issue that the scattering length of electrons in solids seemed unreasonably long. You have all these nuclei with positive charges, And they're all over the place. Every few angstroms, you run into a nucleus with a positive charge. And yet, the electron has a scattering length that can be 100 angstroms, 1,000 angstroms, or 1,000,000 angstroms long. Now, here we have a model where we have lots of nuclei lined up periodically, one after the other, after the other, after the other, and the electron hops from one to the next, to the next, to the next, and makes a wave that goes clear across the system, no scattering at all. You would observe this as a perfectly good wave packet going entirely across the system without backscattering one bit. So that's our first surprising result, and we're going to come back to that result very frequently later on in the term. Okay? Is everyone fairly happy with that? Yes?
So why does it occasionally scatter?
Well, there's lots of other things that we haven't accounted for. For example, we haven't talked about it could scatter into other electrons. So that's actually, in fact, that's something we're not going to discuss all term, because the reason you can ignore scattering against other electrons is actually extremely subtle, and you probably won't even learn it next year. It wasn't understood properly until probably the 1980s or even later. And it wasn't understood at all, not even one little bit, until the 1950s. So that's a really tough question. But there's other things you can scatter. There's impurities, so crystals aren't perfect. There's other junk in it. And there's vibrations. So you can have an electron moving along, and they can hit a phonon and scatter off of a phonon as well. So at finite temperature, there's electron-phonon scattering is frequently the limiting process. OK, good. Good question. I'd give you another chocolate, but you already have one. OK. So we're going to do an exercise we did before, counting states. We did this for when we counted normal modes in our vibrational chain. So we have n nuclei. So that means the length of our system is n times a. And if the length of the system is n times a, the k's we are allowed must be of the form 2 pi over L times p, where p is an integer. P is an integer. You guys familiar with that notation, integer? Yeah? OK, good. P is integer. So the number of different k's, is equal to the range of k's that are different, which is 2 pi over a, the Brouillon zone from here to here, divided by the spacing between adjacent k's, which is 2 pi over L, which is L over a, which is n. Not surprising, the number of different k's we're allowed in the Brouillon zone is equal to the number of unit cells in the entire system. In this case, it's easy to understand that in a different way. We started with a bunch of kets, m. There were n of them, n of these, n orbitals. These were sitting on nuclei, in nucleus 1, nucleus 2, nucleus 3, and so forth. And then we diagonalized our Hamiltonian, and we get eigenstates k, and unsurprisingly, there are n of them, n eigenstates. We had an big N by big N matrix, and we diagonalized it. We got n eigenvalues, n eigenstates. Okay? So you put in n states, you get out n states. One other piece of nomenclature which is fairly useful here, which is this energy scale here, which I guess for our, well, I scrolled it off the top. It's actually 4T. Let's see, where was it? Yeah, so it's 2 times the cosine. 2t times the cosine is the range, and cosine goes from +1 to -1. So the total range from Emax, let's call this Emax here, and let's call this Emin here, Emin here. So Emax minus Emin is known as the bandwidth, which in this case is 4T. Okay. Now, what does the bandwidth depend on? It depends on how much hopping you have. The more hopping you have, the bigger the bandwidth. So let's actually draw a little picture here. What does the bandwidth actually depend on? What does T depend on? Well, the thing we had at our disposal, the thing we could change, was the lattice constant A, the distance between the nuclei. As the distance between the nuclei goes up, the hopping naturally goes down. It's harder to hop over a longer distance. So T goes up, going this way. Good? People happy with that? Okay, and then energy is going to be this way. And then we can draw a picture that kind of looks like this. We start with a bunch of atoms all having eigenstates with energy E atomic. When the atoms are very far apart, they all have the same energy. The electron can sit here, it can sit here, it can sit on any one of the atoms, and its energy is always E atomic. And there are n eigenstates, n eigs. It can sit on any one of the n atoms. Now, as we bring the atoms closer together, as we bring the nuclei closer together, T is going to increase, and we're going to get a band that goes from E min to E max here, and there will be eigenstates within this range between E min and E max. So you pick any energy between E min and E max, and there will be some eigenstates there. Okay? So any energy between here and here, there will always be some k which has an eigenstate at that energy. Now this should actually look a little bit familiar from when we studied the covalent bond. When we studied the covalent bond, we had two atoms with energy. When the electron sat on one nucleus, its energy was E naught, and when it sat on the other nucleus, its energy was E naught. Then we brought them together, and we got an antibonding orbital, antibond, and we got a bonding orbital, bond, down here, one lower and one higher than the original energies. And that's exactly what we have over here. We have a whole bunch of orbitals, all with the same energy. We bring them together, we allow the electron to hop back and forth, and some of the energies go down, and some of the energies go up, and it spreads out into a band. Good? Does that make sense? Yes? Hopefully? So the spreading into a band is coming from the hopping of the electron back and forth. Right. So let's imagine now that we have not just a single electron that we want to consider, but we have many electrons that we want to consider. Since we had n possible k states, but each k state, each k can have two spins, can have spin up or spin down. That means there's 2n total electrons can fit in band. Okay? Good? So we fill up all the k states. You can fill them up with either spin up or spin down. So we can have a total of 2n electrons fitting in that band. So let's first consider a, where am I going to put this? Maybe here. Monovalent atom, which has one electron per nucleus. So that will give us a total of n electrons total, and that half fills the band, half-filled band. Okay? So if we have n electrons total, or one electron per atom, we will fill up the band halfway, up to here. And this is filled now with both spin up and spin down electrons. All right? Now, this picture of a half-filled band, it has some interesting properties. The first thing, one, it has a Fermi surface, What's that Fermi surface? Fermi surface is this point here where the filled states meet the empty states, and this point here where the filled states meet the empty states. So they're just two, since it's one-dimensional, it's actually just two Fermi points, 2 points where you have the highest energy filled state and then there's an empty state nearby. Since it has a Fermi surface, it's possible to make low energy excitations by taking some electron from just below the Fermi surface and exciting it to just above the Fermi surface. Okay? And that means that the heat capacity is going to be proportional to T, like we calculated in the Sommerfeld theory, because you can make as many low-energy excitations. Well, you can make lots of low-energy excitations with no problem. Maybe less obvious, too, is that this is a metal. It conducts electricity. So that's maybe a little bit harder to imagine, but let's think about it for a second. Here what we have is over here, we have right-moving electrons. Maybe I'll label them. Since these guys over here have positive K, h bar K is to the right, so these are right movers over here on this side of the diagram. And over here we have left movers over on this side. So positive versus negative momentum. And if we apply an electric field with very little energy cost, we could take some of the electrons from over here and move them to over here. We could overpopulate the right-hand side by a little bit and underpopulate the left-hand side by a little bit. It costs you only very little energy to do so. Just shift the Fermi surface just a little bit, and then you have a net current. So metal can shift Fermi surface and get current. In fact, the way it actually happens is that you should really think about it. You apply an electric field, and each electron state accelerates a little bit down, in one direction. So each electron changes his momentum a little bit until these guys get overpopulated and these guys get underpopulated, and then you have a net current. So this is indeed a metal. And indeed, it's very, very frequently the case that monovalent atoms are metals. Often, I mean, a simple picture should always be true, but often monovalent materials are metals. Now, further, let's come back over here to the case, to this picture, and imagine what happens when we half fill the band. Okay, so we're going to take this band, we're going to half fill it. Now we've filled these states here, and we've left these states up here empty. So this is the half-filled band. Now, this is very similar to the covalent bond, that it's a lower net energy when the electrons can delocalize between the two nuclei because they're filling only the bonding orbital, and as long as you don't have to fill the antibonding orbital. So here, when you start letting the electrons hop back and forth, they can lower their energy compared to this energy that they started with, this atomic energy that they started with. So there's attractive force between the nuclei, trying to get them closer together, trying to make the hopping much greater. So that is what's forming the metallic bond between, forms metallic bond between the nuclei. This is very, very similar to the covalent bond. By letting the electrons delocalize, by letting them reduce their kinetic energy, by spreading out their wave function, it forms a bonding force that holds the nuclei together. Now, in this very simple picture, we have the same problem that we had when we studied the covalent bond, that by this picture, you would expect that the nuclei would be happier and happier and happier as they got closer and closer together, and everything would go down to sort of zero distance. And that's not true, because some of our approximations start to break down. One of our approximations that starts to break down is that we assumed orthogonal orbitals, that simplifying assumption, that bad assumption that we started with. So that's going to break down. Another thing that breaks down is we forgot about the nuclear-nuclear interaction, which is more or less similar to the covalent bond case. It's more or less canceled by the direct interaction, but when the nuclei start to get very close to each other, that cancellation is no good anymore, and the nuclei start to repel, so they're not going to get infinitely close anymore. But roughly, this is what causes the bonding in metals. It's allowing the electrons to spread out over many atoms and lower their kinetic energy. Okay? Happy? Okay, good. So we can now consider a more general case of divalent atoms. Divalent atoms. I guess not more general. This is just a different case. Divalent atoms like maybe helium. Helium has 2 electrons. In this case, we have 2 n electrons and 2 n eigenstates we can fill. So we get an entirely filled band. Filled band. Well, okay, what happens then? Let's go back to this picture. So now, with a divalent material, we completely fill this band, and we completely fill like this. Everything is filled. In this case, the filled band is very boring. The filled band is inert. Filled band, maybe inert. Why is it inert? Well, if you think about it, is it possible for the filled band to absorb any energy? The answer is no. It can't absorb any energy because all the states are already filled. You can't transfer an electron back and forth from one state to another in order to give it energy or take energy away. All the states are filled. It's a unique state. There's nothing that can be moved around. Can it carry current? It can't carry current because you can't change the number of left movers versus right movers. They're all filled. So it has no heat capacity. No heat capacity. Carries no current, carries no current, and it also has no metallic bonding. And this is, again, very similar to what we had in the case of when we considered possible bonding between the helium atom, between 2 helium atoms. If you have to fill the bonding orbital and the anti-bonding orbital, you don't gain any energy. So here, if we have a filled band, you fill the lower energy states, but you had to fill the higher energy states too. So it doesn't gain you anything to have the hopping go up anymore. Okay, so how are we doing? Okay, good. So as in the case of the vibrational chains that we studied earlier this week, you can also have a situation where not every atom or not every orbital you're considering is the same. So let's now consider a case where there are 2 orbitals, 2 different orbitals per unit cell. And this can occur in 2 different ways, or several different ways. One possible way is that you have 2 different atoms in the unit cell, and they have different types of orbitals in them, sort of a sodium and a chlorine atom or something like that in a unit cell. Another possible case is you have 1 atom, but 2 different orbitals on that atom, like an s orbital and a p orbital, or a 1s orbital and a 2s orbital that you want to consider. So without actually solving this problem in detail, I can show you what the spectrum looks like, what the dispersion looks like. It's very similar to the case of the vibrational chain. So here's k, here's pi over a, here's minus pi over a, here's e. And you get a low energy band analogous to the acoustic mode that we got in the vibrational chain. And you get a high energy band analogous to the optical mode that we had in the vibrational chain. Okay, that's supposed to look symmetric. I apologize about that. So now we have 2 energy bands, the lower energy band and a higher energy band. We could also, if we want, this is the reduced zone scheme. Reduced zone scheme. And we could also draw it in the extended zone scheme, which I'll do over here, actually. Yeah, extended zone scheme. Zone scheme. We could draw the same thing, which would look kind of like this. K, E, here's pi over A. Here's minus pi over A. Here's 2 pi over A. Here's minus 2 pi over A. And the idea of the extended zone scheme is to spread out the bands into two Brouillon zones. So this is the first zone, first BZ here, and the second is out here and out here. Second BZ out here. BZ. Okay, so all I did was I took this piece and moved it over here by 2 pi over a, and this piece and moved it over here by 2 pi over a, such that at each possible k, there's only one excitation. And in either case, this is supposed to line up right at the Brouillon zone boundary. This gap comes in here. This gap comes in here. At the Brouillon zone boundary, notice that there's a gap right at the zone boundary. And it's not coincidental that if you sort of put this together and squint your eyes, this looks like one overall parabola that a free electron might have, but you've opened up gaps at the zone boundary, and we'll explain why that is later on in the term. Now, one thing that you might consider here is suppose the unit cell has 3 electrons. Has 3 electrons in it. Well, then what happens? Then you fill up the entire lower band with both spin up and spin down electrons, and you have half of the upper band filled up to here, and half of the upper band here is filled up half of the upper band. So you filled the lower band and you filled half of the upper band. Well, you'll notice that we have an entirely filled lower band. The lower band is inert. Lower band is inert. And we only need to worry if we're thinking about transport properties or heat properties, specific heat capacity, something like that. We only have to worry about the upper band because the lower band is completely inert, at least unless you give it an enormous energy to excite things out of the lower band and up to the upper band, very high energy because these gaps are typically very large. You can just ignore the lower band altogether and only worry about the electrons in the upper band. But this is actually the answer to one of those questions, one of these puzzles that we wrote down earlier in the term. And the puzzle from earlier in the term was, why is it that you sometimes don't have to worry about core electrons? If electrons are in core orbitals, why is it you can just throw them away when you're counting electrons? For sodium, you only count 1 electron per unit per atom and not 11 electrons per atom when you're trying to calculate the metallic density. And the reason is because basically those other electrons are completely filling bands, and the bands become inert and just aren't part of the interesting physics like heat capacity and conduction. A couple more comments here. So what we've had is that these sort of important principles is that a half-filled band is a metal, usually a metal, and this is for 1 electron per unit cell, or actually any odd number of electrons per unit cell. So maybe I'll say odd number of electrons per unit cell. Whereas an even number of electrons per unit cell, you might think that this is, maybe I'll write might be an insulator. Because you would completely fill bands, and then you have just an inert situation. However, it turns out that there are many, many cases where you have an even number of electrons per unit cell, and yet it's a metal. And the reason that that can occur is if you have a band structure that looks as follows. So if you have a more complicated band structure that looks like this, so here's a k, here's pi over a, here's minus pi over a, and here's the lower band, like this. And then imagine that we have an upper band that does this. Okay? So it's dispersion. More complicated models, you can have a dispersion that looks like this. In particular, the upper band slips below the top of the lower band. So if I have 2 electrons per unit cell, in fact, you could fill the entire lower band, but it's lower energy to partially fill this band and partially fill this band. And that would make up your 2 electrons per unit cell, instead of entirely filling the lower band and leaving these states empty. In that case, you have two partially filled bands instead of one completely filled band. And since you have two partially filled bands, you then have low energy excitations here and low energy excitations here. And so this thing actually becomes a metal. So there are lots of cases of that. Things like calcium has calcium is a metal even though it has 2 electrons per unit cell. And it's exactly this physics that's occurring. The two bands are actually crossing in energy. So instead of completely filling one band, you have two partially filled bands. OK, I think maybe I better stop there. And I see you, I guess, tomorrow.